Yeah, I got registration and it said that this process is going to be slow and because online for registration, it doesn't even show that there's an open spot, so.
I see. Okay. Yeah, there's an open spot on my end, so I just wanted to let you know.
Okay.
Just because we talked last week, so didn't want someone else to get it. So that's why I let you know.
Just waiting for them to put me on.
Professor Trent? You're just. Oh. He's always wearing a jacket. And he's just dripping. That is cold. Okay.
All right, it's 1 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Doing good, doing good. All right, so we're in the second week now. This was supposed to be the first day of class, but everything that happened last week. Funny story, I guess, before we begin today. So, last week I thought I would be off all of last week. Well, not off, I'd be on strike. So, I made plans with my friends and things like that. So, one of the plans that I made was poker. I haven't played poker with my friends in a long time, and so we made plans for Thursday night, thinking that I would be free by 7 o'clock. I'm like, yeah, no problem, dude. I'm on strike. I can make it. Turned out I had to work, and so I ended up being almost an hour late to poker because I get off pretty late on Tuesday, Thursday. I felt really bad because my friends they all brought food and they had like a potluck and everything, and they waited for me to get there before eating. Such great friends, and I felt terrible because I didn't bring anything at all because I was just coming straight from work. Funny thing is, and then after that we ended up playing poker, and I won, and so I was able to go down there, get a free meal, get money from all my friends, and kind of leave very happy. So I felt pretty bad about that, but we all put in the same amount of money, so that's kind of how it works with poker. But now that we're in the second week, we're kind of settling back. I feel like I'm kind of settling back into my normal routine. Hopefully it's the same for you guys. Okay. All right. Speaking of that, so we have a full lecture day. Yeah, question.
Think you're getting invited back?
Oh yeah, of course, of course. How else are they going to get money back from me that way? So I haven't won for like 7 times. So I was due for yeah. Speaking of which, so today we have just a full lecture today. So we're going to pick up where we left off last Thursday. We're going to get through more standard cash flows today, and we're going to talk about equivalents. And so that'll be kind of the main topic for today. Right. Another announcement I have is that homework 1 has been posted. So I posted that maybe about 30 minutes before the lecture today, so you can view that on Canvas. So you probably won't be able to do everything on the homework just yet, but it's due next Friday, and so before next Friday, we'll for sure cover everything that you need to. We'll probably cover everything you need to by this Thursday. So you'll have about a week after this Thursday to finish that. Okay. All right, that's it for my announcements. Are there any questions I can answer before we get started for today? Okay, all right, so let's go ahead and get started. Okay, so we left off last week talking about the concept of interest. All right, so interest is going to be a pretty core concept to us throughout this entire class. So it's good to kind of get an understanding of it. So I think kind of informally, I think the way we kind of defined it last Thursday was that when you have a decent amount of money, or when you have money that you want to use, one way that you can use it, you can invest it, right? Question. So do I post recordings of the previous lectures? I do. So they're on the Canvas site. And so If you have access to the Canvas site, you go down to you on the homepage. You'll see at the bottom of the homepage of the Canvas site, there is a weekly schedule. So week 1, week 2. If you go to each of the pages for like say week 1, there are links within that page to the lecture recordings there. Yeah. Mhm. Okay. So that was kind of our informal definition of interest that we talked about last Thursday, right? And so I think we did one example. I'll just kind of recap that example really quickly. So in the example we talked about last time, you have a friend who has an idea for a business, and so you loan him $5,000. Okay. And so you're going to loan your friend that amount for 5 years. Okay. And so of course, you have a good friend, and so they're gonna give you the money back. But because effectively you're losing access to 5,000 of your dollars for 5 years, not only are you going to earn back your initial investment, the initial 5,000, you're also going to earn interest. Okay? And for this problem, what we said was that you earn 8% interest per year on the initial investment. Okay. And so we just did a very simple calculation. And so if you earned 8% per year, what we computed was 8% of the original $5,000 investment. Okay. So we did 5,000 multiplied by 0.08. Okay. That calculation will get us 8% of 5,000. That amount is $400. Okay. And so through this friend, you're going to earn $400 per year. We multiply this by 5 years. Okay. What we get from this is $2,000. Okay. Zoom's lagging a little bit. All right, so 400 times 5, that's $2,000. So it's there. There we go. It's like a ghost is writing that. And so at the end of the 5 years, your friend's going to give you that $2,000, and he's going to give you back your original $5,000 back. And so if we add our original $5,000 investment, okay, what we get at the end of this is $7,000. Okay. And so basically you turn your $5,000 into $7,000 by losing access to it for 5 years. And so that's kind of one way to think about interest. Okay. So that $2,000, you can think of it as like your fee. Okay. And the idea behind this is quite simple, and it's an idea that I think permeates a lot of just commercial businesses in general. It's the idea that having money on hand right now immediately is extremely valuable. Okay. Because if you're running your business, you can use that money you have right now to purchase materials. You can purchase equipment, hire employees, right? So you can do a lot of things with money on hand. It's so valuable, in fact, that just for the privilege of having money right now, people are willing to pay a premium for it. So they're willing to pay more money to have access to that money right now. And so that's kind of another way to look at interest. And that additional money over time, that's how we define interest. But this is a little bit of a different definition of interest, but this is kind of a more, I would say, a more classical definition than kind of what we did informally last Thursday. Okay. All right. So that example that we just did, the $5,000 convert to 7,000. That's an example of simple interest, right? Where the interest that you compute is only based on the initial investment. Okay. So let's go ahead and define that. So simple interest. Okay. And so in the previous example, what we saw was that our initial investment was $5,000. And so each year we earned interest based purely on that. Okay. So the formula for simple interest is very simple. Okay. We used it already in the problem, but we might as well just kind of formalize the equation here. Okay. So the formula for simple interest is P times I times N. Okay. Where P here is your initial investment, or initial amount, or the loan amount, right? It's you can think of it as the money that you're either loaning out or you're getting in person right away. Okay. This I here represents our interest rate. It represents our interest rate is in decimal form. Okay. And this N here, this N is the number of time periods, either number of months, number of years, the number of times the interest is going to accrue. Okay. Right. So in the previous example, we accrued interest once per year. And so when we loaned our friend $5,000 for 5 years, that N is 5, right? Because we loaned it for 5 years. Okay. So it's just P times I times N, a very simple arithmetic expression. Okay. Very straightforward as well. All right. So the only tricky thing about this equation here is that your interest rate has to be expressed as a decimal. So it's just confusing because a lot of times when you see interest rates, it's given as a percentage. And so, to get it in decimal form, you just have to divide it by 100. Okay. Okay. That's the only thing. And in fact, that's something that we're going to have to do for everything in the class. So today we're going to go over a lot of formulas that involve interest rate, but you can always assume that whenever you see interest rate, it's always going to be in its decimal form. Okay. All right. Any questions on this? Okay. All right. So simple interest is a good place to start. It's always kind of everyone's first introduction to just the concept of interest. But most modern banking practices, investment stuff, they don't work on simple interest. They work on an idea called compound interest. Okay. And so in simple interest, the amount of interest that you get or the interest that you earn is based only on your initial investment. Okay. But in compound interest, another way to look at it is that each period, you're earning money, right? You earn interest. And so in compound interest, just whatever interest that you earned in the previous period gets folded into your initial investment. Okay. Okay. And so the upside of this is that, when you have compound interest, you're going to earn more interest on later periods, right? Because, after one period, you're going to have your initial amount plus the interest you earn from that one. And then the interest that you earn in the second period will be on this new amount, which is greater than it was before. Okay. So to see how this works, I think the easiest way is through an example. So let's do the same example that we did previously, but let's do it with compound interest instead. Okay. All right. Same as before. All right. So just to summarize, let's write down the numbers for everything here. So our initial investment for this case was $5,000. That's money that you're loaning to your friend that is going to pay you back eventually. Okay. The interest rate in this case is 8%, or in decimal form, it's going to be 0.08. Okay. And the number of periods here will be 5 years. Okay. Okay. So in this example here, there's the calculations get a little bit more complicated. So I'm going to summarize it in a table. Okay. You don't have to write this table for all of these types of problems. In fact, at the end of this, we're going to come up with another formula. But just so that you kind of see what's going on in compound interest, we're going to start with the table, and then we'll kind of explain it from there. Okay. Okay. All right, so we're going to have 4 columns in this table. So we're going to have the year. So we have 5 years. So 1, 2, 3, 4, 5. Okay. Each year we're going to have a starting principal, and so each year this is going to be updated based on how much interest we earned from the previous year. We're going to compute the amount of interest that we earned in that period. And then our last column is going to be the new principal, which is going to be the starting principal for the next period. Okay. All right. So let's do the first year all together, just so that you can kind of see what it looks like. All right. So at the end of the first year, your starting principal in that case is $5,000, right? And so that's the initial amount that you lend to your friend. Okay. The interest that you earn from this year is 8% of that starting principal. Okay. We're going to take this amount here, and we're going to multiply it by 0.08. Okay. And so just like we did in the first example, we're going to take 5,000 multiplied by 0.08. That gives us $400. Okay. Then at the end of this year, our new principal is going to be what we started with in the starting principal plus the interest that we earned this year. So we're going to have $5,000 our starting principal plus $400 our interest. And so our new principal at the end of the first year is going to be $5,400. Okay. And then that new principal is going to be the starting principal in the next year. So at the start of year 2, we're going to start with $5,400 instead of 5,000. Okay. All right. So now let's repeat this for year 2. The only difference here is that the amount of interest that we're going to earn that you'll see is going to be greater because we're not starting with 5,000 anymore. We're starting with 5,400. Okay. All right. So let's compute the interest earned. So let's take our 5,400. We're going to multiply it by 0.08. Okay. And so if you have a calculator handy, you can do 5,400 times 0.08. Or you could be like me and you could have written these notes 4 years ago, so you know exactly what this is. And so 5,400 times 0.08 is 432. Okay. Then based on that, we're going to compute our new principal. So 5,400 plus 432, that's 5,832. Okay. And so hopefully what you're seeing here is that through the compound interest, each successive year, we're earning more and more money than we would have if we had just used simple interest. Okay. All right. So then this kind of just repeats itself 3 more times. And so, we'll do the third year. We'll do it fairly quickly. Okay. All right. So in year 3, we're going to start with 5,832. We're going to multiply this by 0.08. This is going to give us 467. Okay. And then we're going to add these together. So 5,832 plus 467. This gives us 6,209. Okay. Then we're going to take that 6,299. We're going to bring it down to the next row. Okay. Multiply by 0.08. That's $504. Add these together one more time. I might be missing some decimal places, and so if you're following along in your calculator, I'm probably missing some cents. But I'm just rounding here just to make it faster. Okay. And so at the end of year 4, we have an amount of 6,803. Okay. Okay. So one last time, we're going to take 6,803, multiply by 0.08. That's going to give us $544. And then our final principal here, 6,803 plus 544. This gives us an ending amount of 7,347. Right. So that's compound interest. And so compound interest generally, if you're the investor, compound interest is definitely more valuable to you because you're almost like constantly earning interest, right? And if you were to invest money in a bank, say in a CD or something, or in stocks, all of those things work on a compound interest basis. So whatever you earn, that gets folded into your principal, and just any future earnings are based on a percentage of that. Okay. All right, any questions on this example here? Okay. All right, and so compound interest is better, and unless otherwise stated. In fact, I don't even think there's any other cases in class. From here on out, we're going to assume we're going to be using compound interest. Okay, simple interest is kind of nice just for introducing the concept, but compound interest is kind of just how the world works. Okay. And so if you see a problem and you see it gives you an interest rate, you can just assume right away it's going to be compound interest. Okay. All right. So how can we compute this, right? And so is there, now that we're using this compound interest concept, is there a formula that we can use to kind of compute this a little bit more easily? Okay. Because the calculations that we just did, we essentially just used the simple interest formula, right? So basically everything in this column here, all of these calculations, right? All of those, we just used our simple interest formula. It's just each time we updated our principal amount, P. Okay. But this was kind of annoying, right? And so this, not the most difficult thing in the world, but still a little bit annoying, especially if you're doing it by hand. And so, there is a better way to do this. There is a formula for this. It's one that we'll use a lot. It's called our compound interest formula. Okay. All right. So this formula looks like the following. So we have F is equal to P times 1 plus I raised to the n power. So let's go ahead and define all the terms here. So our P here has the same definition as in simple interest. So this is your initial principal. Okay. I'm going to give it a slightly different name here just because we're going to move in a little bit of a different direction from here. So another name for a principal or a loan amount is a present sum. Okay. So it's kind of like a new definition there. So a present sum of money represents money that's present, money that you kind of have in the moment, either that you have now in the moment or you're about to borrow in the moment. Okay. Okay. That's why we give it the symbol P. So P, originally we called it the principal, but kind of a more general term for it is a present sum of money, just amount that you have. Okay. I here has the same definition as before, so this is our interest rate. Okay. And once again, it's in decimal form. Okay, so don't forget that. If you don't use decimal form here, you're gonna very much overestimate your investments. Okay. N here, you can see has moved to an exponent, but it has the same definition as before. So this is the number of periods. We have this new symbol on the left, which I've given the symbol F. So the reason I give this symbol F is because this is a future sum of money. Okay. And so just like the name implies, this is an amount of money that you'll have in the future as a result of this investment or whatever. Okay. Make sure you remember that terminology. So we're going to be using that again. Okay, so F stands for future. Okay. And then finally, the last piece of this equation here is the 1. And that 1, there's nothing special about it. It's just the number 1. Okay. But kind of when everything else is simple, it kind of stands out. But you literally just add 1 to the interest rate. Okay. Okay, so we can do the last example in just one single step. We don't have to go through the entire equation here, or we don't have to go through the entire table. Okay. So in our last example, we had a principal amount or present sum of $5,000. Okay. That's money that you have right now that you're loaning to your friend. Okay. Your interest rate, I'm just going to give it in decimal form, which is 0.08, and N is 5 periods. Okay. And so if we use our compound interest formula, we get F is equal to 5,000 times 1 plus 0.08 raised to the 5th power. Okay. And so you plug all those things into a calculator, you get 5,000 times 1.08 raised to the 5th power. And you punch that in, and what you get is 7,347. Okay. So the exact same result that we got using the tables, but we did it just in one step using our compound interest formula. Okay. All right, so when you have compound interest, this is the formula to use. So you don't have to go through the whole table, you can just use this formula here. Okay. All right, any questions on this? Okay. All right, so now that we kind of understand the concept of compound interest, we're ready to move on to the next concept, which is equivalence. Okay. So equivalence, just just based on its name, whenever you have an equivalence between one thing and another thing, you're basically saying that they're equal. Okay. And so and things can be equal in lots of different ways. But when you talk about kind of equivalence in terms of money, in terms of interest rates, what you're really finding equivalent is, the value of money in 2 different points in time. Okay. Listen. Okay. So what do I mean by this? And so, if you remember on Thursday, we kind of started this kind of whole discussion by talking about how money has a time value, right? Money that you have right now is more valuable than money that you have in the future, right? Think about the $100 example, right? And so if you had the choice of getting $100 now versus $100, a year from now, that $100 is going to have a lot more value now than a year from now, right? And so, when you're comparing amounts of money in different points in time, you can't just compare their raw amounts because, that value of money is going to change with time. Okay. So for example, okay, I keep coming back to this example just because there's a lot of information we can glean from it, right? And so if we think back to the $5,000 that we lent our friend, right? Let's think about this just kind of purely from our perspective, okay? And so that $5,000, that's money that you have on hand right now, okay? if we compare this to, if we took that $5,000 and we invested it in our friend's business, and granted that we trust our friend and he's not going to, leave the country after 5 years, he's going to pay us back, right? And so after 5 years, that $5,000 is going to be worth $7,347. Okay. What we can say from this statement is that $5,000 is equivalent to $7,347 in 5 years. Okay, so these two amounts are equivalent. Okay. Granted that we know the interest rate, right? And so these two amounts are equivalent at an interest rate of 8%. So this kind of represents the idea of equivalence, is that, when you're comparing money or amounts of money in two different time periods, right? Even compared to today and tomorrow, right? That $5,000 that you have in your pocket right now, it's not going to have the same value tomorrow, right? Because what can happen in a day, right? In a day that, you could have taken that $5, you could have invested it in something, right? Your return on it would be very small, but it would be, greater than if you just had that $5 in your pocket. Right. Same thing with the price of goods, right? And so that $5,000, maybe, you can go get a sandwich for it today, but tomorrow, they may raise the price on the sandwich. Right? And so things can change with time. And so when you're talking about amounts of money and different points in time, right? You can't say that they're equivalent unless you know the interest rate or the rate at which that amount of money can grow. All right, so all of these ideas are linked. So the idea of compound interest, money growing with time, and having that future sum be equivalent to a present sum, at a given interest rate. Okay. All right. And so what we're going to do from here is that, we're going to introduce different forms of cash flow. So we're just about done with the basics, and so we're just kind of comparing single lump sums of money in two different points in time. But soon we're going to factor in, what if you have a recurring payment, a recurring revenue, right? How does that factor in with interest rates, and how does that factor into this idea of equivalence? Any questions on this so far? Yeah.
So we get into this, but is there a specific set interest rate for inflation?
Yeah, no, it's a good question. We'll cover inflation in a lot more depth, kind of near the tail end of our economics unit, so probably in about 2 months. But interest rate definitely changes, and so it depends. I mean, the exact interest rate depends on just a lot of different things. And we'll learn how to deal with problems where the inflation rate kind of changes with time, the interest rate kind of changes with time as well. Exactly. Yeah. Yeah. It can get kind of messy. Okay. So before I do, just because it's useful, it's kind of implied by the formula that we have. But let me go ahead and write our compound interest formula one more time. Okay. So that right there is our compound interest formula. Okay. One way that you can look at this formula, or one way to interpret it, is that it can take a present sum of money, you can take a P and then convert it to a future sum, granted that you know the interest rate and the number of time periods. Okay. Okay. And so you feed in a P, you give it an I, you give it an N, and then you get an F out of it. Okay. So it's converting a present sum to a future sum. You can very easily kind of rearrange this formula. And so let's say that we want to solve for P instead. Okay. And so if we divide both sides by 1 plus I to the N, okay, we can get the following formula. We get P is equal to F divided by 1 plus I to the N. So this formula is just a very simple rearrangement, but then it's the way you can kind of use it is a little bit different. Okay. And so this kind of gives you the reverse. And so, if you plug in everything on the right side of this equation, this converts a future sum to a present sum. So in the case where you're given an F and you need to compute a P, then this is how you would do. Okay. So very, very quick, simple example to kind of show you how this is used, right? So this formula that I've just boxed here is very common when you want to save, for a big purchase, right? So I think very commonly, people put in money away into an investment into stocks to save to buy like a car or something, right? So let's say that after 5 years, you want to have $1,000 in a certain bank account. Okay. Let's say that this bank account has an interest rate of 2%. Okay. So each year, the amount of interest you're going to earn is 2% over just whatever's in the bank account at the time. Okay. And so the question for this example is how much, if you're just going to make one deposit. So let's say you're just going to make one deposit today, and you're just going to let that money kind of passively grow over time. If you want to have $1,000 after 5 years, how much money do you need to put in today? Okay. Right, so this is kind of the opposite situation than our previous example. And so now we're given $1,000, but that $1,000 is an amount that we want to have in the future. So this $1,000 is actually an F. Okay. We're given the time period. So our N here is 5 years, and our interest rate is 2%. Okay. So let's just kind of plug everything into the formula above, and then we can compute the present amount. Okay. All right, so the amount that we need to put into this bank account now is the future amount, which is 1,000 divided by 1 plus I, so 1 plus 0.02 raised to the 5th power. Okay. So we're dividing by that amount instead of multiplying. And so you just punch that into a calculator very simply. And what you get is $905.80. and 73 cents. Crazy. Laggy internet. All right. And so if you have a bank account, it gives you 2% annual interest rate, 2% APY. If you put in $905 in 5 years, you will have $1,000. Okay. Right. So that's not bad, right? So for not doing anything, you earn about $95 on an investment. Granted, you can't spend that $1,000 for 5 years, and that's kind of the price that you pay. But what you get at the end of it is more money than. Okay. Yep. Yeah. Mhm. Yeah, not too much, but it's something, for not doing anything, right? All right, any questions on this example here? Okay. All right, so we're done with kind of P's and F's now. And so, we're done with kind of single sum money. If you remember from last Thursday, one thing that can happen very commonly in engineering projects is that you have recurring expenses, recurring benefits, right? You have revenues, you have maintenance costs. And so of course, those payments and those types of cash flows will be affected by interest rates as well. So let's start talking about that. Okay, so the next type of cash flow that we're going to learn is one called a uniform series. Okay. So present sums and future sums, P's and F's, I consider those to be kind of lump sums of type of cash flow. So they're just kind of one-time payments, one-time benefits that occur just in one point in time. Okay. But it's very common, not just in engineering projects, but in general, to have recurring cash flows. Okay. And usually these recurring cash flows occur at fixed amounts of time. Either you pay these every month, you pay these every year. There's a fixed amount of time in between each payment. Okay. So there's two types of recurring cash flows that we're going to consider. So the first being a uniform series. So a uniform series is a recurring cash flow with the same amount of money in each recurring expense. Okay. The other type of recurring payment that we'll go over is something called an arithmetic gradient. And so that is a recurring payment that actually grows in time. But we're not going to be able to get to it today. So we'll probably cover that on Thursday. Okay. But let's talk about uniform series first. All right. And so when you're talking about recurring payments or recurring cash flows, the question always arises in terms of, when do you assume these? Okay. If you remember from last Thursday, when we talked about our cash flow diagrams, when we had things like our revenues, our maintenance costs, we always assume those to take place at the end of the time period. Okay. We're going to make that same assumptions here. And so when we draw our cash flow diagrams, the amount that we're going to have is at the end. Okay. So one type of uniform series that we're going to encounter a lot is a maintenance cost or a maintenance payment. Okay. And so maintenance cost is going to be the same amount that recurs in every period. Okay. And so in this diagram here, in this cash flow diagram, I've given each time period a recurring amount of A. Okay. So A is our uniform series amount. And A is the symbol that we're going to use. And so, we've already been introduced to P, present sums, F, which is future sums, and A, which is uniform series. Okay. The reason we give it the symbol A is that usually a lot of expenses are kind of considered on a yearly basis. And so A stands for annual cash flow. Okay, so that's kind of where it gets the okay. Okay. Any questions on this so far? Okay. All right. So now that we've now that we're introduced to the idea of a uniform series, the next question that we can ask is, can we convert, or how can we convert between a uniform series and present sums, a uniform series and future sums, with compound interest in mind? Because between present and future sums, we had that formula, right? We had our compound interest formula, and that was able to convert between a present sum and a future sum. Okay. It would be great if we can have such a formula for uniform series as well. And turns out it does exist. But let's do a little bit of a derivation to kind of show how this comes to be. It's a short derivation, don't worry. And it's very visual. So okay, so let me go ahead and draw a cash flow diagram again. Okay. And let me draw a uniform series, but just kind of for the sake of variety, let me go ahead and draw it going up. Okay, so each of these up arrows here is the same amount of money. So we're not taking interest rates into account yet. We're just going to assume that over a four period time horizon, at the end of each period, we're going to pay an amount of A. Okay. Okay. So for now, let's consider each of these as kind of a single payment. Okay, so even though eventually we want to group all of these together into one calculation, just for the sake of this example here, or this derivation, we'll consider each of them to be a single future sum. So we're just gonna, we're gonna look at each arrow individually as if they were kind of an individual one-time sum. Okay. All right. So what I want to do is I want to convert. So let's convert each of these individual one-time sums. Let's convert them all to overlap on the same time period. Okay. So this is something that we can do, right? Because if we consider each of these as individual sums of money, then we can just simply use our compound interest formula from before to convert them to a different form. Okay. And the reason we want to convert them all to the same time is so that we can add them, right? Remember the concept of equivalence is that if you're comparing amounts of money in two different time periods, you can't really count them as equivalent. So in order to do things like add, subtract, you have to convert everything to be at the same time so that you can do that. That's a very important concept that will, because of interest rates, you can't add monies at different time periods. You have to convert them all to the same time period before you can add stuff. Okay. All right. So we have 4 conversions that we need to make. Okay. One for each cash flow. And what I'm going to do is I'm going to actually push all of these into the future. So let's convert all of these to a future sum occurring at year 4. Okay. You can very easily convert all of these to a present sum. That works fine as well. It's just the math works out a little bit. There's less decimals if you push them all to the future. Okay, so let's see what this looks like. So let's start with the first one here. So let's start with the amount, the single amount of A in time period 1. Okay. Okay, so if we were to push this to year 4, we're going to move it forward 3 years into the future. Okay, because in order to go from year 1 to year 4, that's 3 years. Okay. And so we're going to use our compound interest formula. And so we're considering this as just a single sum of money. And so the amount of money that's present on year 1 is A. Okay. Then we're going to do 1 plus I. We can assume the interest rate is given to us, but you'll see it's going to kind of cancel out at the end. Okay. Okay. And so if we were to convert that single sum of money in year 1 to year 4, the formula we would use is A times 1 plus I raised to the 3rd power. Okay. So that's the first one. Okay, next let's do the amount in year 2. Okay. We'll call this F2. Once again, we're going to use our compound interest formula. So we have F2 is equal to A times 1 plus I. Right. Going from year 2 to year 4, we're only going 2 years in the future, right? So it's going to be A times 1 plus I squared. And then we can do the same thing for F3. So F3 here, we have A times 1 plus I. Going from year 3 to year 4 is just 1 year in the future. So this is just going to be raised to the 1st power. And then finally, we have the last sum. And so we have an amount A in year 4. That's already in year 4, so we don't have to do any conversion. And so we just have F4 is equal to A. Okay, so we don't need to convert in that case because we're already in the right time. Okay. So now we have F1, F2, F3, F4, right? So through these formulas here, we've converted those those cash flows all to the same time. We pushed them all to year 4. Okay? So now that all these are in year 4, we can simply add them together to get the total amount of money or total amount of cash flow from that diagram. And so our F in this case, so F being the total future sum amount. Okay, this is just going to be F1 plus F2 plus F3 plus F4. Okay, so we can add them all together because they're all in the same time now. Okay, and so if we plug in for those, it's a little messy, but we have A times 1 plus I the third power plus A times 1 plus I squared plus A times 1 plus I plus A. Okay. So that's what that formula would look like for 4 periods, right? Of course, this relationship isn't unique to just 4 periods. We can generalize this. So let's say that we have a uniform series that occurs over n periods. Okay, so any amount of time, this relationship will still hold in that case. Okay, and so for n periods, we get F is equal to A times 1 plus I to the n minus 1 power plus A times 1 plus I n minus 2 power plus. Okay. So that's going to continue. I'm not going to, continue ad nauseum there. But at the end, our last 2 terms are the same. So we keep counting n down, and eventually you're going to reach the n, which is A times 1 plus I plus A. Okay. So that dot, dot, dot represents kind of a lot of terms in the middle there that, at this moment in time, I'm too lazy to. Okay. All right. So we're not done quite yet, but let me just, well, I'll pause here. So let me just kind of underline this. Okay. Because I think, with these kinds of derivations, it kind of gets, it's a little bit easy to get lost in the details. And so it's always good to kind of pause every now and then and kind of remind ourselves what we're hoping to achieve. Okay. Okay. So eventually what we want, is a relatively simple relationship between F and A. Okay. That also incorporates the interest rates and the time period. Okay. So in other words, we want something similar to our compound interest formula, except instead of F and P, we want a formula between F and A. Okay, just so that we can kind of easily convert between the two. Okay. All right, and so if you look at what we have right now, if you look at the expression that's underlined, we're kind of there, right? So we have the right components, and so if we look at that expression, we have F, we have A, we have I and N. They're all present, so all the right players are in place. It's just a little bit cumbersome right now because it's first of all, it has this ellipse. which kind of represents that basically just represents things that the writer is too lazy to write. Okay. And there's also, an unspecified number of terms. And so, our next step here is, now that we have all the right players in place, let's see if we can kind of simplify this expression using some tricks or mathematical stuff. Okay. All right. Any questions on this so far? Okay. All right. So how are we going to simplify this? We're going to simplify this expression. Whenever you have an infinite series like this, and this next piece of information is kind of more just applied math stuff, so not really super relevant for this class. But what you have right here is a series, right? It's a summation of a lot of terms. And so one trick that exists in math to kind of get rid of this is to subtract it from the same expression. You just multiply by something else. Let's subtract. So we're going to subtract this exact same expression, except we're going to multiply it by 1 plus I. Okay. And so unless you're really into math, it's going to seem like I pulled that trick out of my ass. And honestly, it kind of is like, it kind of is just pulled out of your ass, but then it works really well in this expression because it's you have kind of that series of summations. Okay? So basically what we're going to do is we're going to come up with another expression. Okay. And so instead of f, we're going to have f times 1 plus I. Okay. So we're going to take that entire underlying expression and multiply it by 1 plus I. So we have f on the left-hand side, we have f times 1 plus I. On the right, we have a. So this works out really well because all of the parentheses components are in exponents that kind of decrease by 1. Okay. And so when you multiply by the same thing, you just kind of increase the exponents by 1. So we have a times 1 plus I to the n, a times 1 plus I to the n minus 1, plus dot, 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 plus a times 1 plus I squared, plus a times 1 plus I. Okay. So it's the same expression as the first underlined one. It's just that everything is multiplied by 1 plus I. Okay. Okay. And so if we call that second expression 1, and we call that top expression 2, okay? What I'm going to do is I'm going to do an equation subtraction. So I'm going to take the entire expression of 1 and subtract 2 from it. So we're going to subtract, let me kind of clear this out here. We're going to extract f is equal to a plus 1 plus I n minus 1 plus a times 1 plus I n minus 2 plus dot, dot, dot. Okay. So I'm going to subtract these two equations from each other. Okay. So I'm going to subtract the left-hand side from each other. So f times 1 plus I minus f. And then I'm going to subtract the entire right-hand side. Okay. All right. So why am I doing this, right? So the main reason I'm doing this is mostly to get rid of these ellipses right here. Okay. So I want to get rid of that just so that we can get a simple expression. Okay. Because what you should see here is that a lot of these terms are going to cancel out. And so if we look at just the left-hand side of the equation, okay, and if we distribute this, okay, and so up top here we have an f plus I times f. Okay. If we take this and we subtract f, the F's are going to cancel out. And then at the end of the day, on this left-hand side, all we're left is I times F. Okay. So that's looking really good. Okay. On the right-hand side, this is where things get a little bit more complicated. But what you're going to see is that a ton of these terms are going to cancel out. In fact, everything is going to cancel out except for two of these terms. Okay. So for example, let's look at this top here. So this top here, we have an a times 1 plus I raised to the n minus 1. And then on the bottom here, we're going to subtract an a times 1 plus I to the n minus 1 power. Okay. So those two things are exactly the same, and so they're going to cancel out. Okay. Same thing with this one. And so on the bottom there, we have a times 1 plus I to the n minus 2. Okay. You don't see it up top because up top, it's actually part of this ellipse here. Okay. So this one's also going to cancel out. In fact, everything in that ellipse is going to cancel out. Okay. Okay, and if we look at these last few terms here, we have an a times 1 plus I raised to the first power. Up top there, we have an a times 1 plus I. Those ones are also going to cancel out. Okay. And then all we're left with is an a times 1 plus I to the n and an a. Okay. So let's go ahead and write those into the equation at the bottom. So we have a times 1 plus I raised to the n minus a. Okay. All right, so that was an extremely mathy derivation, but now that we've arrived here, now it's very simple to do because now that we have this expression here, let's just simplify this a little bit. Okay. So you can simplify it in a couple of different ways. I'm going to do kind of the straightforward thing. I'm just going to divide both sides by I. Okay. And so if we divide both sides by I, we get F is equal to A multiplied by quantity. So I'm going to factor out A from that side. So we got 1 plus I raised to the n power minus 1, all divided by I. So this formula right here, this here is our conversion between a future sum and a uniform series. So the future sum being F, and A is a uniform series amount. Okay. All right. Any questions on that whole kind of derivation there? Okay. So I know the question on everyone's mind. I don't make you guys do derivations on homeworks or exams or anything. So this derivation here was just kind of for your information. But I don't personally, I don't like kind of pulling equations out of my ass. And so if I were to just show you this equation right here, it would have no context at all. And so I wanted to show you that everything that we've learned so far about compound interest can be applied, and we can get a new formula for this. We do have 2 more minutes left. So before we go, I do want to show you a very, very quick example of just how this is used. Okay? So this one I'm actually pulling out of my app because the next actual example I have is too long. But one way that this formula is used is, when you guys all graduate and you guys all have jobs, you'll have the option of putting money away for retirement. Okay. And so one form that this takes for a lot of people is called a 401k or a retirement account. So the way a 401k works is that you basically take a percentage of your paycheck and you invest it at a certain interest rate. Okay? There's a lot of other rules and restrictions with these in terms of like, the amount of money you take out is pre-tax and then it grows and then you pay tax later, but I'm not interested in that. So kind of one thing that people are interested in is that, if you're going to set aside money in each paycheck, how much money are you going to get in retirement? So this is a perfect example of this formula here, because the amount that you're setting aside in each paycheck, right? You get your paycheck at regular intervals, and so that will be a uniform series, okay? And so this A here would be like your 401k contribution. Okay. Sometimes you'll work for a nice company, which will match your contribution, so you can add your company's contribution to that. Okay. Your I here is your interest rate. Granted, it's hard to estimate an interest rate because these are probably computations you're going to be doing over a 30-year horizon. Okay, but you can get an average interest rate. Okay, and here is usually the number of years, and so this is a the amount of years until you're going to retire, 30, 40 years. And then F here is the amount that you can withdraw once you retire. And so if you're going to look at like an online calculator for like through Fidelity or whatever your bank is for this, using a formula kind of similar to this to compute those things. Okay. All right. Any final questions for today? Wait a second. The tax will be on your retirement amount, but because at that point you'll retire, so it'll be lower amount. Yeah, we'll go over taxes. Don't worry. Okay. So thank you guys for coming today. Hope you guys enjoy the rest of your day, and I will see you guys on Thursday.
Right?
Yeah.
Yes, okay, so I just gonna go to this, and then I was just wondering, like, what have I missed last week?
Okay. Yeah. So once you get access to the Canvas site, I think it should give you automatically.
Okay.
You'll be able to see that you can access the recordings. I didn't assign you. There's one assignment I did last week, which is just send me an email. The first real assignment I just and that's gonna be due next Friday. But yeah, it's all on the Canvas site, so I can show you real quick. Yeah, because last week I did a tour of the Canvas site. Thank you guys. Have a good day. Okay, 401. Let me do student view. Mine has a lot of stuff. So this is the home page.
Okay.
You're going to come down here. You'll see that at the bottom of the home page, there's kind of a weekly organizer here.
Okay.
So if you go to each of the weekly pages, so if you go to week 1, you'll see that there are links here to watch the lectures. So this will just take you to YouTube, and you can watch the lecture from last week. So there's a Tuesday lecture, Thursday lecture. Homework 0 this is the introduction. So this is just instructions for the email. And then all the lecture notes for that week are here as well.
Okay.
And then for this week 2, I usually post the lecture recordings the next day, so this will probably be up tomorrow. But here you can see this is the homework 0, which is just the introduction. And this right here is the first real homework assignment. So you can download the problem set here. And you can do it, but that's not due until next Friday.
Next Friday. Okay, got it.
But yeah, that's about it. And then, yeah, once you're on the Canvas site, you'll start getting announcements too.
Okay, great. Thank you so much.
Yep.
Hello.
Hey,
I'm still not in the class because there was like issues with my enrollment.
uh,
So it kind of like, I was on the wait list, but it skipped over me.
oh, I see.
And now it's, I saw it this morning, I was like, oh, the class is open. I was like, wait, I'm not in the class, and now it's waitlisted again.
Yeah, so I know, because I think they increased the amount of seats in the class at 38.
Yeah, I
And
saw
38 is actually the max for this classroom, so we can't go
Oh.
above 38. But the problem is for the other section of 401, that one's also at capacity, because that one's at a different room that has a max capacity of 36. So that one's also maxed out. And so I mean, you can stick around if you want, if someone's gonna drop. I think it's a little bit less likely now.
No, not really.
Now that we're at the second week. Yeah, and so you can either take, I think there's open sections of 401 from the other engineering departments, so like civil engineering, electrical engineering, I think has openings in their 401 course.
I tried looking, but I didn't really see anything that was open.
Oh, really? Okay.
Everything's pretty much waitlisted.
Oh, dang. Okay. Send an email. Do you have our department chair's email address?
No.
Okay, so his email address. I'll tell you what, let me give you our advising email address, and then I'll kind of follow up with you afterwards. So
It's the BSM.
yeah, BSME advising. So go ahead and send an
Okay.
email to that, say that you need to take 401 this semester. I need to look at your study plan again. Maybe there's another class that you can take instead of 401.
Okay.
But if not, I could talk to the other departments and see if they're willing to add more students. But I know for this course, for this section, we're at capacity. We literally can't add more seats because the fire marshal will delete.
Be mad.
Yeah. And then I think the other section's also at capacity too, but we'll see what we can do.
Okay.
Yeah.
Also, if I do get in the class, I want to let you know that the last week of February, I'm going to an academic conference.
Okay, sure.
I looked at the syllabus and I'm pretty sure it doesn't like line up with any midterms or anything, but I still wanted to let you know just in case.
Sure. Yeah, no problem. Yeah, I mean, just catch up with the lectures when you get back. So
And you don't grade by attendance.
no,
so
no.
I don't have to worry about that.
no.
Okay, cool. Thank you.
Yep.
Have a good rest of your day.
Thanks, you too.